Everybody good with that?
Yes.
Okay. Let's say we're falling straight down. Let's say it rolled off this way. It's just like free fall, right?
Yeah.
Boom. What if I want to find the final velocity that way? It's at rest right there to fall, right? The final velocity this way.
Acceleration.
So initial velocity, final velocity, what's acceleration going to be?
9.8.
Okay. What's the, what else do I know? The height, right?
Yeah.
Okay, that's h. Okay. If I know a displacement or a height, I know initial velocity, looking for final velocity, and I have acceleration. What equation would I use up there?
The first
The
one.
first one, right? Displacement, acceleration, final, initial, final, whatever. So if I did that, I have VF squared equals V naught squared plus 2G H in this case, right? Delta Y or delta X EH. A is going to be G, okay? What's my initial velocity?
0.
0, so I'm going to get rid of that. VF squared equals 2GH. If I'm going to get VF, what do I do? Does that look familiar? Hey, it's the same equation.
Physics is.
There.
Why'd you like cross out V naught squared?
Because we said its initial velocity was 0. So 0 squared is 0. So, okay. So it's the same exact equation. What does that tell you about something's final velocity going down a ramp versus just falling? Same. Same final velocity. You know what the difference is?
Speed.
It's the same velocity, right?
The distance it covers.
The distance it covers.
What?
So they would have the same velocity, but would they reach the ground at the same time?
No.
No, because this one's going to be speeding up more slowly. It's going to be a gradual acceleration
Over a longer distance.
over a longer distance. Quicker acceleration over a shorter distance. Because this is acting basically as a component. Is that making sense to you?
A little bit.
Okay? All right. So conservation of energy, we can use that to solve for all of the stuff that we did before. If all we know is the height, we can get the final velocity, and we don't have to worry about getting the x and y components.
You just gotta know the equation.
Yeah. Because I could tell, we could look at this angle, we could figure out how fast it's going horizontal and how fast it's going vertical.
True.
But using conservation of energy, we can solve it just like this. Boom. Beautiful, huh?
It is
Yes.
just exquisite.
Yeah. Okay. So let's do this with real numbers. Okay? Let's do it with some real numbers. Let's say the mass is equal to 5 kilograms. Let's say the height is equal to 30 meters. What's the final velocity of the ball when it gets down to the bottom of the ramp?
You want this?
First things first.
Yep, I want you to solve it.
Let's get it.
What about data? Do you not get data?
I'll give it data. 32 degrees.
Wait, but we don't need data.
You don't need data.
Is it
I know, it just makes you feel
12.25?
better.
I like to get to know data.
How'd you get it?
I like
did
data.
30 times 5 and the square root of, or well, 30 times 5 is 150 and the square root of 150 is 4.25.
30, which is height, times 5,
Wait, why do you do double
No, I don't know, what the
which
fuck?
was
And
mass. And then you took the square root?
Wait, but the equation is 2GH,
Oh.
not, has nothing to do with mass.
Don't listen to me, I'm.
You're being
I
really good, that's all. No,
I tried,
we're also
I
good
tried.
sometimes.
So what was G?
You want 9.8 or 10?
10 or 9.8? What's half of that?
5.
Or pardon me, not half. What would I do with that? I would make 2 times G, right? Times the height.
I was so proud of myself.
So 2 times 10 or 9.8, whatever, times 30. So you got 60 times 30, how much is that? Or 20 times 30?
600.
600.
Then you square
Okay.
it.
So take square root of 600, and what do you get?
24.26.
There you go. All right, so